Hi, this is Christian. So I'm going to demo the dots and boxes game. So it's running number of squares per dimension. We'll do 2. Number of plies to look ahead. So the max it can do without the heap overflowing for a 2x2 grid is 6. So we'll do that. The game's starting. So the AI moves first, and he chooses the bottom dash. So the player selects a dash by index, and it's ordered from top to bottom, left to right. So 0, 1, 2, 3, 4, 5, 6. So if I do 0, I get that top one. I do 1, I get the other top one. Okay, so I think we've seen enough of that. And then if we do a 3x3 grid, I'll just do 2 plies for this. It's the same thing. Okay, so for the actual code, this is main. We ask the player the number of squares per dimension, the number of plies to look ahead, and then I use a builder to create the game, and it sets all that. And the heuristic is, this is for evaluating the leaves. It's the AI score minus the human score. So obviously, if the AI has an advantage at that point. Okay, so for the game, I modeled the game win scenario as an exception. You'll see that in a little bit. So start game, we have a grid state. It's initially empty. There's no dashes filled in. We print it out. And then the actual game is, of course, a loop. So the AI makes a move. There's a new state. That becomes the new current state. The human makes a move. That becomes the new current state. And you keep looping until that exception is thrown, the game over exception. And then you can calculate the scores. And if the human is greater than the AI, of course, they win. Otherwise, the AI won. I'll skip the AI move for a second. The human move, it's very simple. It just takes in their dash index selection and then make sure it can make that move, and then it makes that move, which returns a new state. So let's go back up to AI move. So the AI move function, it will actually wrap up the state in a game node, which creates the entire tree up to the horizon from that point. And then using that game tree, it runs the min-max algorithm, and it uses alpha-beta pruning, which is why I send in these 2 arguments. We'll see that in a second. And then min-max returns the best move value. And using that value, we look at all the children and find the move to make. And it makes that move, and then that is the current state. So the min-max algorithm, it's what we talked about in class. If the current node distance to horizon is 0, in other words, it's at the horizon, or if it's the final state, then calculate the heuristic, and that's its min-max value. Otherwise, we're going to actually do the algorithm. So if the current turn of this node is the AI, which is max, then we go through the algorithm and we find the max so far. And of course, if that's greater than the beta of an ancestor, then we're done. Because the local max only gets bigger and bigger, but there's no point to keep examining these nodes. And that's the exact same for min, except the complement. Yeah, so min is essentially the exact same, except we're... Okay. So as for how the grid state is actually modeled, there's a list of dashes and a list of squares. And the dashes are essentially what you can fill in from top to bottom, left to right. And then attach dashes to squares. It essentially goes through all the dashes and it makes a square out of them. For example, this square is going to take an upper dash, a left dash, a right dash, a lower dash. This is just an easier way to assign scores to the human player and the AI player to see if they've claimed a square. So make move, it essentially makes sure you can make that move, that you could fill in that dash, and then it actually creates a new grid state doing that move, and it returns it. Is final state, it checks if all the squares have been awarded to a player, and then of course the game's over at that point. 2 strings, really complicated, but I'll skip over that, it's not important. So game node, of course, it wraps up grid state, and this is for the AI making decisions using the min-max algorithm. It knows its parents, it has a list of children, and so it actually does this recursively, so it generates successors. And what does that do? Well, it sees if you can draw a dash, and if you can, then you basically add to the children list. And of course, if you're at the horizon, or if you're at the final state, then you don't generate successors. Okay, so dash is very simple. Is it drawn? Yes or no? And yeah, that's about it. And once you draw a dash, it checks the square it's a part of, and if it fulfilled that square, then it awards it to the player who made that move. And square, it knows the player it's awarded to. It's null at first, nobody has a square, and it's assigned a random score. Okay, that's about it.